All right, we are now recording. Let's start from the current slide. Sorry, we're 5 minutes late getting started, but I called rolling that kind of stuff. So, there are a few announcements. I think you've heard them before, but maybe not all of you have. So let me go over those. And my computer's not talking. I don't know why. If I don't plug it in, it won't pick up. It's a mystery to me. Is it going to pick up now? Oh, man. There it comes. Yes. Okay. You've heard most of these before, but let me say them again. This class has been very good about getting in the first test. Okay? Okay, maybe a little on the low side of getting in research papers, but, 3 of you have done that. First test, I'm still missing 2 students. Otherwise, I would return your first test to you. Neither one of those 2 students is here, so I'm preaching to the choir here, but Caitlin is here, and so is Bree. Okay. I think I marked 3 here already. That meant I got somebody off. Yeah. All right, let me go back through there. I'm off on my thing. All the way at the end of the page, that's right. Cerinthia's not here. Ryan's not here. That's where I messed up. Put Jemiah 1 down. Okay, now everybody got you in the right place. Okay. What I was saying is 2 people haven't turned in the first test. Only 3 have turned in the research paper, but 2 have not turned in the first test. Neither of them are here, so like I said, I'm talking to the wrong group. But usually after midterm, which was Tuesday at midnight, okay, they ask for us to do midterm progress reports. So if I don't have a score at midterm, I have to say you have an F at midterm. That doesn't really mean much, except that you might start getting bugged by people saying, well, do you need tutoring? Do you need counseling? What can we do to get your grades up and stuff? So if you don't want to be hassled with that kind of stuff, then please get me some paper in. And like I said, last time I checked, I didn't see anything about midterm progress report, but they sometimes flop it on us and say it's due right now, so anyway, we'll go with that. Now, number 2, normally on Fridays, like tomorrow, I'm on the Birmingham West Campus from about 8 till 12. Usually they're before 8 and they're after 12 most days. Not tomorrow. Tomorrow I will be leaving home hopefully before 7 o'clock in the morning and driving down to Mobile for a 3 to 3.5 hour meeting and then driving back. So that's going to be about a 13-hour day for a 3.5 hour meeting. So it's going to be a pretty rugged one. I will not be on either campus at all. I'll be leaving home before 7 and getting back probably after 8. So no way I'll be on either campus at all. So if you were going to try to get in touch with me, don't bother tomorrow. Now next Friday, also I have a little bit of a problem, not a big one. I have an eye appointment just across the street here at the UAB West Hospital, their eye clinic there. I thought they were going to get the Callahan Clinic downtown or south side, but they said, no, he's on this one. I said, well, I work right across the street, so there's no problem. So I will be seeing him at 8:15 next Friday morning. So I'll be on this campus ever so briefly and then have my eye appointment. And then if I can, after the eye appointment, I'll be going to Birmingham West Campus then. I just don't know what time. I'm guessing around 10. I don't know, maybe plus or minus from 10. All right. Can't think of anything else urgent now, so let's go with it. Any questions of yours? Anything on anything we've covered so far? Okay. All right. We got started on 5.1 last time. Oh, and does everyone here get the copy of the second test? Okay, good. The choir again. Okay. Don't start singing, Christian. Okay. The using fundamental identities. Okay. What's that? Yeah, it is. You can't see it. Oh, here's why. I have too many lights on. Still can't see it. Huh. It's right there. You can just barely see this. And I don't know why it's not showing up. I can see it here, but I guess it's off out of the range or something. All right. One common application of trigonometric identities is to use given values of trigonometric functions to evaluate other trigonometric functions. So we may know something about one, but we need to know something about another one. Very similar to stuff we were doing in the last chapter. So here's example 1. It says use the values that secant u is equal to minus 3/2 and the fact that tangent u is positive to find the values of all 6 trigonometric functions. Well, we know 1 already, so we've got 5 to go. All right. Now, before we go anywhere with this, is this even reasonable? Is secant ever negative 3/2? Is that a valid value for secant? Anybody? Yay or nay? Make a guess. Yes, yeah, it's a good guess. If they gave it to us, no problem. Yeah, remember secants are always from +1 up or from -1 down. This is in -1 down. So yeah, that is a valid thing. Okay? Now, the other thing to note here about secant is the negative. Can secant ever be negative? Well, I just said that's the now. Where is secant negative? In which quadrant or quadrants is secant ever negative? First? Yea or nay? No. Everything's positive in the first quadrant, so it can't be in the first quadrant. U cannot be in the first quadrant. Okay? Where is secant, or can secant ever be negative? Where is secant negative? Second? Quadrants 2 and 3. So this minus sign here says that U has to be either in quadrant 2 or 3. So don't even mess with 1 and 4. That would not be true in 1 or 4. Now, it says tangent U is positive, though. Where is tangent U positive? 1, everybody's positive in 1, but we already know we can't be in 1. Yes, tangent is positive in the third quadrant. So therefore, since the first quadrant's out, because we can see it being negative, we know we are in the third quadrant. Because tangent's positive there, secant's negative there. All right, 2 clues. Okay, sounds like Blue's Clues, right? Never mind. Y'all wouldn't know that long before your time. Okay. Now, they want all 6 trigonometric functions. Can anyone tell me what those 6 trigonometric functions are? Sine of u, cosine of u, tangent of u, cotangent of u, secant of u, and cosecant of u. Okay? And Devin came in, right? Right. Now, do we know any already? Secant u is negative 3/2. All right. All else we know is that tangent's positive. Well, then we know we're in the third quadrant. Okay? Now, which of these remaining trig functions is the easiest to determine if you know that secant u is negative 3/2? Cosine, yeah. Why? What would cosine be then? the reciprocal of that, which would be negative 2/3. Perfect. Okay? So we know cosine u. Two down, 4 to go. Okay? Now, given that, nothing else is going to be super easy, but it's not bad. Okay? Now, I know what the book wants you to do. It wants you to use the trig identities. Okay? Because it says at the top, using identities to evaluate a function. And we sort of are using them, but here's a far easier way in my mind. We already determined we're in the third quadrant, right? And we could have used secant, but I like cosine better. What is cosine in terms of x, y, and r? What is cosine? Is what? Adjacent over hypotenuse. Now, which of these would be the adjacent and which would be the hypotenuse? The two numbers there, a 2 and a 3. Which would be adjacent and which would be hypotenuse? Negative 2 would be the what? Adjacent. You're absolutely right. Now, this is not technically using a trig identity. So negative 2 is the adjacent, and adjacent is always the x, right? So x is negative 2, and what we have, though, is a 3 circle. Not a unit circle, but a 3 circle. I know that's not what you're supposed to call them, and I don't draw circles well, but let me sort of do one in here. And we know we're in the third quadrant, and the adjacent value is negative 2, and the hypotenuse is 3. Okay? The question is, can anyone tell me the y value? Please say yes. Oh, it would help if I put the adjacent in the right place, wouldn't it? And nobody caught me on that, did you? Huh. Whoops. Can't get my pen to write. Okay. There's the adjacent side. Negative 2. Any idea what the opposite would be? Anybody get it? Yes, the Pythagorean theorem. And what would that be? Second? A little louder. Okay, x squared plus b squared equals to r squared. Okay, where r is 3. Okay, and so the x is minus 2. Minus 2 squared is 4. 3 squared is 9. The difference between those is 5. So this has to be the square root of 5. Okay. Now my picture isn't drawn to scale because this should be a little bit longer than minus 2. But that is also what sign? SIGN sign. We're in the third quadrant. It's not root 5, it's negative root 5 because you're in the third quadrant. Okay? Both of your x and y's are negative there. Now with this drawn, hopefully we can write all the other trig functions down. What in the world is sine? Okay, and what would that be? Negative root 5 over 3. Tangent would be? Okay, he said negative root 5 over negative 2. I agree with that. It would be root 5 over 2. I agree with that. Because guess what's positive in the third quadrant? Tangent. So it has to be positive. Remember that was given. Okay? What would be cotangent? Second? 2 over square root of 5. And frankly, I'm happy with it left like that. But if you don't like having radicals in the denominator, how else could you write it? 2 root 5 over 5. Perfect. Okay. All right. And we got one left. Cosecant. Oh, no. Can we do that? Oh, that would be minus 3 over root 5. And if you don't like radicals in the denominator, what would that be? Negative 3 root 5 over 5. There, we found them all. Now, we did use trig identities in that. We used that tangent was the ratio of these two, and that cotangent was reciprocal of that one, and that cosecant was reciprocal of that one. We just didn't use the one they wanted us to use here, which was that sine squared plus cosine squared is equal to 1, because it was so much easier to do it here. And then you could have done them all from here if you wanted to. Tangent was opposite over adjacent, and cotangent was adjacent over opposite, and secant we already knew. Cosecant was hypotenuse over opposite. We could have done them all from here, but that was still using trig identities, just in the simplest form. Okay? Does that make sense? Now, if you like using the identities and going back to Pythagorean identities and doing it that way, certainly okay. We use Pythagorean theorem to get this, and that's where the Pythagorean identities come from, so same source, same thing. Any questions on that? Does it make sense?
I have one question.
Okay. Too late. No, I can never reply.
B, you got negative square root 5, right?
Yeah, right here. How or why? Is that what you're
I was
asking?
just asking. That's what you got.
Yeah, that's what you got because you're down there in the third quadrant. And that everything points to that. You know, you have, well, you're in the third quadrant, so that has to be negative. And that's why I drew the axis here and didn't just do this quadrant.
Oh, I see what you're saying. So you whenever you do the Pythagorean theorem, you get positive.
Yeah, because you're squaring, yeah. A squared and B squared.
I was thinking I did something wrong.
Yeah. Yes.
So I don't know if I just missed this or what, but I understand how you get where you find integration is negative and all that because all students take classes. But how do you find the reciprocals? What quadrant?
Okay. You know, all students take calculus, right? All is all of them.
Yeah.
S is sine, T is tangent, and C is cosine. The reciprocal of those are the same signs.
Okay.
Yeah. So that would be cosecant, sine and cosecant here, tangent and cotangent here, so you get both positive, and secant and cosine both positive. Yeah. Good question. Excellent questions. All of them. Any others? Ask them while they're hot. Okay.
So this is the ones that are positive.
What's that?
You said those are positive?
Yeah, that's where they're positive. All of them are positive in the first quadrant. Sines and cosecants in the second quadrant, all students. Tangent and cotangent is reciprocal in the third quadrant, all students take. Calculus is cosine, and its reciprocal, which is secant, in the fourth quadrant. Everything else is negative in those three quadrants, except those two that I mentioned. And all of them are positive in the first quadrant. Good deal. And you can also do that by the coordinates, you know. Hypotenuse is always positive, okay? And then the first quadrant, both the adjacent and the opposite are positive, so everything has to be positive. Over here, it's only the adjacent that is negative, so that would be only cosine and secant negative. Oh, no, I'm sorry. Everything with the adjacent in it, okay, would be negative here, which would be a cosine, a secant, a tangent, and a cotangent, because they all have adjacent in it. Down here, both everything's negative. I mean, your x and y are both negative, so the only thing that depends on that, x and y, or adjacent and opposite, would be tangent and cotangent. That ratio would be positive. Okay, and over here, only your y's are negative, your x's are positive, so the thing that depends on y, the sine and the cosecant are negative there. The tangent and cotangent also depend on the opposite side of the y. So those are negative too. Okay. Strange way to think of it. Just trying to give you several ways to think of it. Let's see how they did it. I'm sure it's going to be a little different. Any questions before I leave the slide? Okay. Good questions, by the way. Very good questions. So what they did using reciprocal identity, yeah, that was the easy one. cosine is 1 over secant, so therefore it's going to be 1 over negative 3 halves. I'm glad they're showing all these steps, and that would be negative 2/3. Yes. And that also makes sense because sines and cosines have to be between plus and minus 1, and that sure enough is between plus and minus 1 on the minus side. Okay? Now, what they do next is the Pythagorean identity. I just used the Pythagorean theorem on my little triangles and got the same result. So sine squared is 1 minus cosine squared, so you have to square cosine squared, and that gives you, and they skipped a lot, but they said, okay, yeah, okay, just, okay, all right. So in here, right? All right. Now, they skipped a little bit here. 1 minus a negative 2/3 squared. A negative 2/3 squared would be positive 4/9. 1 is 9/9. 9/9 minus 4/9 is 5/9. So that's how they got that. That's going to be sine squared. So you have to take the square root of that. When you take the square root of that, you get the square root. Because secant is negative and tangent positive, you have to be in quadrant 3. We did that to very begin with. Okay? So since you have the sine squared being 5/9, that means sine is either plus or minus the square root of 5 over 3. Okay? Well, quadrant 3, sine's negative, so you have to choose the negative side there. Negative SIGN side. Moreover, because sine u is negative in quadrant 3, choose the negative square root, which would be negative root 5 divided by 3. Okay. Now, to me, that's a little bit longer way to do it than the way I did. But if you see this better, go for it. Use it. It's right. Okay. Knowing that all the values of sine and cosine enable you to find the values of all 6 trigonometric functions, sine being minus root 5 over 3, cosine we already determined to be, then they do cosecant. They like doing it this way. So that would be negative, wrong, okay, they put negative 3 over 2, that should be negative 3 over root 5. Okay, sorry about that. And then to correct that, they to get the radical out of the denominator, we made it negative root 5 over 5. And again, cosecant sine, always the same sign, SIGN sign. Okay. Then cosine, we already knew was negative 2/3. And that, when they're wrong, they're consistently wrong. Okay. So this is negative 3 over 2, which is what they gave us in the beginning of the problem, so it can't be that. Okay. Duh. And they didn't change that. I don't know. All right. I'm pretty sure it wasn't the math people doing this. I think it was the graphics people. The tangent is sine over cosine, and that's why I like writing one like this, because all I do is draw a line here, and then notice that the denominators divide out, and you have negative 5, positive 5 over root 2. I mean 5 over 2. Negative, positive root 5 over 2, if I can say it right. Here. Okay, and then the cotangent is so easy. Just flip that over, and you get 2 root 5 over 5, or 2 over root 5. Good deal. Graphics are wrong, but their answer's right. Okay. Make sense? All right, here's example 2. And by the way, every example is followed by a checkpoint. Good idea to do those as soon as you can after class while it's sort of fresh on your mind. It says, simplify this expression. Okay. I don't think any of you are going to have this problem, but in case you are tempted at some point, there's no solution to this. You're simplifying it. The only way you can get a solution is you get it equal something. Okay? This is not an equation, it's an expression. All it says is to simplify. So how could you simplify that? What's one thing you could do to simplify? Right off the top.
Divide sine x.
Okay, yeah, factor out a sine x, okay? So let's factor out a sine x. And what are you left with? Cosine squared x minus 1, you said? Okay, very good. Now, can you simplify that any further? This is going to take a little bit of, say, imagination. Does that look awfully close to? What's that?
Doesn't it look like one of those identities or something?
It's very similar to an identity. Not quite the identity, but very similar. Anyone remember which one that might be? Okay, here's a hint. If it has a square in it, think Pythagorean identities. Those are the ones with the squares in them, right? So what is the simplest Pythagorean identity? Very simplest one, the most straightforward one. Starts with sine squared x. Anybody? Can you finish this for me?
Sine squared plus cosine squared.
Plus cosine squared x. Get to know these folks. These are your friends. Okay? Equal to what? Always. Okay? Now, I can subtract a cosine squared x from both sides. Okay? That goes away, and you're left with a sine squared x is equal to 1 minus cosine squared x. That looks like this, but not quite the same. What's wrong with it?
You don't have those two sine x's.
Okay, well, no. Okay. No, this thing right here looks very similar to that. What's the only difference? How do you make it change? This second? Yeah, factor out a negative 1. That would do it. So if you factor out a negative 1 here and a negative 1 here, this is, hang on to this a minute. Just factor it out here. Minus cosine squared x minus 1. Okay. This would be sine squared x, right? Because you just factored it out. You didn't change anything. I don't want the minus 1 there, so let's multiply both sides by minus 1. Right? Now, this becomes sine x times negative sine squared x, and that becomes, help me, negative sine cubed x. That's about as simple as we can simplify it, I think. Right? Make sense? Okay, get it to as few terms as possible, simplest form as possible. So let me erase my chicken scratch, and let's see how they did it. First, factor out the common monomial factor, which happened to be a sine x. And then they noted that that was exactly, boy, did they do it strangely. They factored out the minus 1 here, but moved it over here. Gave them that, and then that was minus sine x times sine squared x, and that became minus sine cubed x. Any way you do it, as long as all the steps are right, you should get the right answer. Does that make sense? Yay or nay? Okay.
Go back so
What's that?
go back so I can copy
Oh, I'm sorry.
no,
Huh?
to the work you had done.
Okay, I erased it. Sorry. Catch me sooner, folks. Once I erase from the screen, it won't come back. But this is the same type stuff. It just did it slightly differently. That works just as well. All I did was do the Pythagorean identity over there and scratch through that and saw it was minus sine squared. And then I had sine x times minus sine squared. And it still get you minus sine cubed. All right. Now, when I did advance, I saw it jump to example 7. All right, so they skip 3, 4, 5, and 6. So let's pick up with example 3. So we're going to have to write these out. So let me, if no one's using this, was anyone still copying this? Okay, everybody got it? Okay, then let's back up. We'll use this slide to do example 3. Factor each expression. Here's one. Secant squared theta minus 1. And before you factor, I do want to ask you this. What is secant squared theta minus 1? Anyone remember? Make sure I'm right on this. I believe I am. Is it that tangent squared theta? Because tangent squared plus 1 is secant squared, right? So subtract 1 from both sides, you got that. Well, that's beside the point here. They said factor it. Does that factor? Yay or nay? Hint. That's a perfect square, right? That's a perfect square, right? And that's a difference of two perfect squares. Ring the bell? How does that factor? Yes, sine or secant theta plus 1 times secant theta minus 1. That's it. That's all there is to that. Okay. This next one, just maybe a tad more involved, but not too bad. We have a 4 times a tangent squared theta. My screen decides to move on me every now and then. Plus tangent theta minus 3. Can you factor that? Here's a hint. Treat the trig function as if it's a variable. Just think of it as if it's a variable. Rather than being x, it's tan theta. Okay? It's just a long variable. Tan theta. Okay. Now, if this is factorable, it's a trinomial, right? And if that's factorable, think of that as being 4x squared plus x minus 3. If that was factorable, and we don't know that it is, but if it is, what would be, there's now a couple of possible factorizations for that first term. What you think it might be? Name one. How would 4 tangent squared factor? 4 and 1, okay. 4 tangent theta, he's looking ahead, aren't you, times tangent theta, okay. Okay, now that may not be the right factorization, but it is a correct factorization. Now where we look next is the sign of the last term. What's that? And what does that tell you about these two signs? They've got to be different. So which way you want it? Plus minus or minus plus? I don't care too much. Plus minus, okay. Is he looking ahead? No, he's not. Okay. Plus minus. Okay. Now, what's a factorization of 3? Oh, yeah, 3 and 1. In that order? He is looking ahead. Okay. Now, let's see if that's the correct factorization. Let's foil it. First, it's foiled again. 4 tangent times tangent is 4 tangent squared. That works. 4 tangent times minus 1 is minus 4 tangent theta. And 3 tangent times 3 times tangent theta is a plus 3 tangent theta. Uh-oh. Those had to be minus tangent theta. We have a plus. Okay, here's my hint. If you got the wrong sign, change signs. If you have the wrong number, change numbers. Okay? But you got the right number, you just got the wrong sign, so let's make this one the minus and make the other one the plus. Okay? Now, let's start back again. Our first term is still right. Okay? I'll go erase it all. Okay. All right. 4 tangent times tangent is 4 tangent squared. That works. The outer is now a positive 4 tangent theta, and the inner is a minus 3 tangent theta. Those add to be plus tangent theta. And that is your middle term. How about the last? Minus 3. Yep, that's the factorization. 4 tangent theta minus 3 times tangent theta plus 1. And that's all we're doing. Just factoring. We're just simplifying. And we're happy because we got a happy face now. We got it right. Right. Okay. And that's what they got to. Good for them. All right, there is a checkpoint there. Please do the checkpoint. All right, let's move on to example 4. Does anyone need this a little bit longer? Yay or nay? Everybody got it? Okay. So let's do example 4. These are kind of fun, aren't they? Factoring a trigonometric expression. Here's one. Cosecant, oh, one of my favorite. So, secant squared x minus cotangent x minus 3. Uh-oh, SpaghettiOs. What's wrong with this one? Yeah, the functions are different. How can you factor that? And the answer is you can't. Okay? Not directly anyway. So what might we do? Think identity. No. You have some identities that have squares in them and some that don't. I think I would. And which one would you use? 1 plus cotangent squared x is equal to cosecant squared x. Y'all remember that one? I'll look it up. Okay? So instead of cosecant squared x, we're going to write 1 plus cotangent squared x minus cotangent x minus 3. That's a little awkward, but at least we got the same functions. But what do we need to do? Yeah, combine like terms of plus 1 and the minus 3. That adds to, is what?
Cotangent squared.
Okay, yeah, cotangent squared. Okay, yeah. Good deal. Thank you. Okay, cotangent squared x minus cotangent x, those don't change any, minus 2. All right, now what it said was factor it. That looks like it might be factorable. No guarantee it is, but at least you got all the same functions. The other was like a x squared minus y plus 3, or minus 3. You can't factor that. Now that you got them the same, you might be able to. What's the only factorization of cotangent squared? Cotangent times cotangent. Okay? Then we look at the sign of the last term. So what's that? So we're going to make one a plus and one a minus. And then what? A factorization of 2. What's that? 1 and 2 in that order? He's either looking ahead, looking at work, or something. Okay. Now, let's check it and see if it works. Don't just assume, just because all the individual numbers work, the whole package has to work. So cotangent times cotangent, sure enough, is cotangent squared. That works. Okay, then you got a minus 2 cotangent and a plus 1, and that's going to add to a minus 1. Minus cotangent, yes, and then the last is minus 2. That works. Okay? Happy face again. Any questions? All right? They got cotangent x minus 2 times cotangent x plus 1. The order doesn't matter. Okay? You got it both. All right, let's move on to example 5. Is there any questions on this one before I erase it? Everybody got it? Okay. No one needs it any longer. Okay? Now, example 5 is one of those that they have a little saying, italicized print under it. See larsonprecalculus.com for an interactive version of this type of example. You could actually go and see and interact with them and see what happens. What you have here is, they don't say what to do, they just write it down. At the top they say simplified, but let's see. Sine t plus cotangent t cosecant t. No, that's a cosine t. I can't read. Cosine t is equal to, really? Sine t. Oh, they're working the problem for you. Gag. Okay. Not going to have you do that. Oh, the 10 o'clock scholar. Okay. Ryan's here. Okay. All right, so we're just missing Cody and Dimitri. All right, they haven't come in, and Lindsay and Stephanie. They haven't come in. I think pretty sure that Cody has a baseball game today, is where he is. Because I had 4 players in my first class, and all 4 of them were absent. They're always there, so I have a feeling that's where Cody is now. Okay, this is our problem. They didn't do anything else. They just wrote it down, and then they started working on it. How would you work on it? I don't want to know how they would. How would you do it? This is 3 different trig functions. So what would you do? Now here's my fallback. If I can't see anything obvious, like factoring out a common factor or using Pythagorean identity or something like that, when I have something like this, I can't think of anything else to do, my fallback is get everything in terms of sines and cosines. There's nothing you can factor here, and this one's already in terms of sine. That one, part of it's in terms of cosine, but the other part isn't. So what would you do then? Whoops. Sine t stays sine t. Okay, that's already in terms of sine and cosine. What is cotangent t in terms of sines and cosine? Cosine t over sine t. Okay, and this is times cosine t. Ew, that actually looks worse, doesn't it? Okay. Second? You could, and that was going to be my next step. This is the same as sine t plus cosine squared t over sine t. Now, what's sort of messy about this one? That one's got a denominator, this one doesn't. Right? How can we get a denominator here but not change the value there? Okay, right now, okay. Okay, that's a denominator. Okay, now that's an addition with different denominators. How do we add fractional forms with different denominators? Common denominator, and what would that have to be? Sine t. So how do we get a sine t here instead of that 1? I'm going to erase the 1. How do I get a sine t there? Say again? Okay, multiply numerator and denominator by sine t over sine t, right? That's 1. You can multiply by 1 anytime you want to, so it'll make this, like Ryan said, squared over sine t down here. Does everybody see that? Okay, that's exactly right. Now what can we do? put them, add the numerators over the common denominator. So that would be sine squared t plus cosine squared t over sine t. That looks sort of familiar. What's sine squared t plus cosine squared t? 1. That's your Pythagorean identity. So 1 over sine t. But what's 1 over sine t? That's cosecant t. I don't think we can get any simpler than that, can we? So you got something that was really messy looking at the top, an expression with 3 different trig functions in it, okay? And you got it down to 1 trig function. There was 1 multiplication and 1 addition there. You just got the function itself here. That's pretty much simplified, right? Any questions on that? Just notice in the book, that's what they got to. And they have a checkpoint for you to look at. Any questions on that one? All right. That's clear. And go to example 6. Perform the addition and simplify. So here we have a sine theta over 1 plus cosine theta plus cosine theta over sine theta. Okay. It says perform the addition. Before we can perform the addition, what do we have to have? Same answer as before. You need the common denominator. What would be a common denominator here? Say again?
Denominator of the sine theta and make it 1 plus cosine theta squared.
Okay. What I thought I heard you saying, tell me if I got it right, it's a product of these two denominators, like 1/3 plus 1/2. There's nothing common between them, so you multiply them together and you get 1/6. That'll be your common denominator. It will be the least in this one too. So you multiply them together. So in other words, on this one, you need to multiply by sine theta, right? To make it common. So let's multiply by sine theta. But if you multiply the denominator by sine theta, what do you better do the numerator? Multiply by sine theta as well, so that makes it sine squared theta. Okay, but over here we're going to have to multiply by 1 plus cosine theta, but we'd better multiply the top by 1 plus cosine theta as well. Okay, so now we got common denominators, so we can add our numerators together. But before we do that, I hate writing again, but I will. I'm just going to write this down. Sine squared theta over sine theta times 1 plus cosine theta plus, now here's what I'm doing. You may think it's not fair, but it is. I'm not multiplying, I'm not distributing my denominators. I'm going to leave those factors, but I am going to distribute my numerators because I think that'll help. Okay? So what is cosine theta times 1 plus cosine theta? Cosine theta plus cosine squared theta. All right. And that's over sine theta times 1 plus cosine theta. Again, I'm not distributing my denominators. Okay? Now, what I'm going to do here is we got least common denominator, so I'm going to keep the denominator, add the numerators. Right? Sine squared theta plus cosine theta plus cosine squared theta, that's adding my numerators together, over sine theta times 1 plus cosine theta. Got it? Are we through? Have we oh, what can we do now? Look for identities. Say again? Second? Oh, here's a Pythagorean identity right here. They're a little bit separated, but they're still there. Sine squared theta plus cosine squared theta. What's that equal to? 1. So you have a 1 plus cosine theta over sine theta times 1 plus cosine theta. You see why I didn't want to distribute by denominator now. What do you notice now? Sorry. Y'all awake yet? All right, good. Okay, got you. All right. What can you do here? Yes, divide out the 1 plus cosine theta. And you're left with 1 over sine theta, which guess what that is? That's cosecant theta again. They seem to like cosecant theta a lot more than I do. Okay. So that's cosecant theta. Now, did you ever think that the last problem we did, sine t plus cosine t, cotangent t cosine t, was equal to this thing, you know, before we multiplied through? It doesn't look like it was anywhere close, but they are exactly the same value. Okay. Any questions? I see some squinting, so I want to make sure I answer any questions before I leave it. Is that confusion or just trying to read the board? Okay. My ugly handwriting, I understand. Okay. All right. It doesn't hurt too much. Okay. Got it? Any questions? Everybody got it? All right. That took us through example 6. The example 7, I think, will be on the slide set, so let's scroll down till we get there. And here we have example 7. It says, rewrite this expression so that it is not in a fractional form. In other words, we don't want a denominator. Okay? Excuse me just a second. Maybe all legitimate. There's someone in the office. What's that? I think they must be doing another one of those building surveys type things. Okay, Dimitri is here. All right. We're just missing Cody, who I think has a ball game, and Lindsay and Stephanie. They may be cheering for the ball. I don't know. I'm just kidding. Okay. So, we need to get rid of the denominator. So, I'm going to write this down, 1 over 1 plus sine x. Look like what? Oh, it doesn't look that much like it, does it? Okay. You can only divide out things that are multiplied. Those are added. Can't do that. Please don't. Okay. All right. So, now, here's a trick. And as my calculus professor said, when I took calculus, we were on the quarter system. So I had 5 quarters of calculus, and then the 6th quarter was differential equations. And I had the same, I was really fortunate, I have the same professor for all 5 of the quarters of calculus. And on the 5th one, he was hard, and he covered fast. And then we actually finished almost a week early. You know, it was a 10-week quarter, you know, maybe part of a week early. We met 5 days a week. He said, well, since we finished everything we need to cover in this, let me get you ready for differential equations. That was the next course coming up. And so he started telling us some things about it and showing us some things. He said, really, in differential equations, what I found is best is if you can't figure out what to do, try a trick. And if the trick works more than once, call it a method. And sure enough, that seems to work okay. So I want to show you a trick here. It's not a new trick. It's one you've used before, but maybe not in this context. Does anyone remember what a conjugate is? We've already used at least one today. That's when you multiply by the same thing, but with an opposite sign. 1 minus sine x. Now, you can't just go and do that unless you multiply the numerator by 1 minus sine x. Okay? There is a method to the madness. It may not be obvious yet, but there is. What does that denominator become? Now, earlier I wasn't touching denominators, but this one we got to do something. What does that become? The numerator is just 1 minus sine x, because you multiply that by 1 and you just get that. Okay? What does the denominator become? 1 minus sine squared x. You're absolutely right. That one, I started to write a theta. So I love thetas, you know, but you write x like it's supposed to be. Okay? That is when you multiply the sum times the difference, same two numbers, the conjugates, you get the difference of their squares, which we had earlier. Okay? Now, the reason we did that, what in the world is 1 minus sine squared theta? Think identities. Second? Cosine squared theta. You're absolutely right. So this is 1 minus sine x over cosine squared x. Now, you might, yes? How did I get from here to here? That's the Pythagorean identity. One of them, one expression of it. The main of Pythagorean identity is this one. Sine squared x plus cosine squared x is equal to 1. That's always, 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 always true. Okay? So if you subtract a cosine x from both sides, you get sine squared x. Or, subtract sine squared x from both sides, you get a cosine x squared x. Right? All right, so that's how we got it. Now, we're one step closer to having it not in fractional form. You see, here we had a binomial in our denominator. Those are hard to convert. Now we got a monomial. Hey, we can deal with that. In fact, here's how I suggest. Now let's split this into 1 over cosine squared x minus sine x over cosine squared x. Right? Would you agree that's a legal step? It's sort of what we did on the earlier problems going the other direction. Rather than getting the least common denominator and combining, we've got a common denominator, let's split them. Got it? Everybody in favor of that? Yay or nay? You happy with it? Now, does anyone know what 1 over cosine squared is? Just secant squared. You're absolutely right. Secant squared x. There we got rid of that denominator, right? Minus. Now, a little bit of scratching on the side here. Sine x over cosine squared x is the same as sine x times 1, right, over cosine x times cosine x, right? Would you agree that's true? Okay. What's sine over cosine? Say again? Did I hear a co there or not? It's tangent. Sine over cosine is tangent x. And what's, not tax, that's coming up later, okay? It's tangent x. It's really bad when I do secant x and get that, leave out the end that I see there. Okay, never mind. Okay, tangent x. And what's 1 over cosine? Secant. Okay, we did what they told us to. We got that in not a fractional form. Now, there's some other things you could try to do, but I don't think they're going to help any. You could factor a secant out, and then you'd have a secant x times secant x minus tangent x, but that's not going to get any simpler. So I think that's as far as they want us to go. Let's see what they did. Yep, that's what they did. Secant squared x minus tangent x secant x. Got it. Any questions? Okay. You see, you lost the denominator and got it into a lot more complicated, but at least there's no denominators. Okay. I'm going to erase this and let's see if they did it any differently. I think they did it pretty close to the same. Let's see. From the Pythagorean, okay, they went from this route, which to me is kind of, you have to know what your answer is before you get there, and that's sort of hard to do. Whereas if you take it one step at a time, you're just trying things and seeing if it will work out. But because they knew that, then they said, okay, well then let's multiply by the conjugate. And they did. Maybe you think, well, I knew that too, but that's just a good trick to do. If you got something you don't know what else to do with it, try multiplying by a conjugate. But you have to multiply by 1, so it's 1 over that. So they got just like we did, and then they noted that because they had already noted that's cosine squared, so it's 1 minus sine x over cosine squared x. Then break that into the two separate fractions, 1 over cosine x minus sine x over cosine x. And then note that that's 1 over cosine squared x minus the sine x over cosine x times the 1 over cosine x. That's what I did off to the side. And then the first term is secant squared x minus, and the first factor there is a tangent x, the second is a secant x. Done. Woo! And that's the last slide of the day. I mean, of the section. There are two more they didn't do, so let's back up and do those two. Any questions on that? I can go back to it. This I can go back to. I can't go back if I erase it. Any questions? All right. So let's do example 8. They're going to tell us what to do, and we're going to do it. Okay? Well, like me, right? Okay, never mind. Use the substitution x is equal to 2 times the tangent of theta. Now, where did they come up with that? Hang around for calculus. Probably Cal 2. Yeah, Cal 2. And you'll see where they got this. Okay? Now, this is good for 0 less than theta less than pi halves. Okay. Now, I can't tell you any specific reason that they made it theta greater than 0, not greater than or equal to. No real reason, they just did, but it's fine. How about this part, though? Could they have put an equal sign under that? Could that have been less than or equal to? Anybody? Can tangent ever be, can you ever take the tangent of pi halves? No, why not? Tangent is sine over cosine. What's the cosine of pi halves? 0. Can't ever divide by 0. So that's why this has strictly less than. This one could have been less than or equal to. That's fine. But they just chose to do it less than. You couldn't have an equal sign under that. Okay. So that's what we're going to use to rewrite this expression. The square root of 4 plus x squared as a trigonometric function of theta. Okay. And frankly, I can almost hear you saying, why would you want to? Okay. That looks like a perfectly good form to me. And it is. There's nothing wrong with it. Unless you are trying to integrate it. And then you have no chance of integrating that in that form. None. None whatsoever. So we're going to do what they call a trig substitution to see if that makes it be anything a little bit better. So instead of x, we're going to put in a 2 tangent theta. Well, they have here an x squared. So if x is 2 tangent theta, what in the world is x squared? Anybody? 4 times tangent squared theta, right? You square each of the factors, right? Now let's put that in for our x squared. So we have square root of 4 plus, instead of x squared, we put in 4 tangent squared theta. Okay? Now what do you notice you can do with that? Factor out a 4, right? Okay? That would be the square root of 4 times 1 plus tangent squared theta. Everybody buy that? Now guess what 4 is? A perfect square. So you can pull that out. Square root of 4 is 2. So that's 2 times the square root of 1 plus tangent squared theta. Does that look at all familiar? What in the world is 1 plus tangent squared theta? I've only hit it about 2 or 3 times today.
Oh, that's good.
Yep. It's what? Yep. Pythagorean identity. Say it. Secant squared. You got it. That's the same as secant squared theta. And guess what the square root of secant squared is? Square root undoes a square, right? So that becomes 2 times secant theta. Yep. There we rewrote this fairly complicated looking form into a form of function of theta. And guess what? We may not be able to integrate that either, but at least we can look that up in a table somewhere. Okay? So, sure enough, you've simplified. You got rid of square root, you got rid of squares, you got rid of sums, you just got a simple multiplication there. All right. Any questions? Okay. And that is indeed what we've got. And it's really good that you're less than pi halves again, because secant can't be pi halves again. Okay. I take it by all the relative motion that we must be out of time. Is that right? Oh, I won't. Yeah. Oh, yeah, we are. Shucks, how did the time fly? And unfortunately, I've got to go pretty quickly because I've got to go pick up a vehicle for my trip tomorrow. And they didn't have the paperwork this morning, even though I turned it in last week. So hopefully they'll have it now. So we'll pick up next time with example 9. And we won't even go to section 5.1, so don't let me do that. Thank you so much. Don't let me do. Did you get the second test? You. Okay. Did everybody else get the second test? Okay. It's in here somewhere. Okay. And you need graph paper.
Yes.
Okay. It requires graph paper. Now this is front and back, so if you can get 4 on one side and 5 on the other, fine. If not, ask me some more graph paper. All right, excellent. Thank you so much.
Did you see my paper?
Huh?
I emailed my paper to you.
Oh, you did?
Yes.
When was it that you emailed it?
Last week, I think.
Let me see if I got it. I've graded so many papers lately. I think I did see it, but I don't know if I printed it off. Well, let me see. I think it's in here right now. I just didn't. Wait a minute. Corinthia, is she still out there? She just turned in test 2. I gave her test 2 again. If you can catch her, let me see.
I never got this to you.
I think I printed it because I ran across it today and said, you know, I never got that graded.
I don't really know what she looked like, so I just
She's the one that was just in here. She just walked out. I thought she was turning in test 1. I asked her if she had test 2, and she said no. I gave her test 2, and now I just noticed her graphs.
No, it's in the beginning of the chapter. It's like,
Can I do test 2 as well?
There you are. I got it. It's just in the wrong page. I got it.
Is it written the way you want it to?
That's what I got.
Okay, well, let's
Is
hope
that
it's
what
right.
you intended to send?
very first page.
Yeah, that's what I said, but
Okay.
I hope that I did it correctly.
Right. It looks fine. It's longer than it needed to be, so it's great.
Okay, and then test 2.
Oh, you didn't get. She has your copy of test 2 because that was my last copy. That's why I didn't know it was you that needed it. She didn't come back, did she? No.
Nope, she did.
Okay.
All right, well, I'll get
I'm gonna have to go make another copy. Sorry. Yo, not yet. Yeah, I'm gonna try. See, this has been a crazy week. I'm not gonna be on campus tomorrow, so ask me Tuesday again. But hopefully Monday
I'll
morning.
probably end up sending you an email. To try.
Okay, that might work. It may not.
I may not.
Yeah. Okay. Let me see. Here's test 2. Do you need graph paper? Wait. Do you need graph paper?
Yes.
Okay. You want me to go make a copy for you?
For test 2?
Test 2.
Sure.
Okay.
I'll wait.
Okay. What did you have? Okay. You asked me a question or
About Pythagorean theorem.
is that one of them? Yes, it is.
Is it? I mean,
Well, yeah. This is one right here, right?
I didn't know that was one.
Yeah, it is. 1 plus tangent squared is secant squared.
That don't make any sense.
Exactly.
That
Right?
doesn't make any sense.
What's that?
It doesn't make any sense.
Well, is sine squared theta plus cosine squared equal 1?
Is cosine what?
Sine squared theta plus cosine squared theta equal 1.
Yes.
Yes, of course. So divide every term by cosine squared.
Okay.
Sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is secant squared.
I'm gonna write that down.
Okay.
I'm gonna write that down.
Okay.